Send me an email if you're interested. I'm gonna send you the program. And you can get TCTS for the obviously courses. So, are we early? Can we start?
We can start. Yeah, it's 15.
We can start. Okay. What else? There is some specifications. I want some kind of stuff I want to say about what I said last time. So, yeah, let's write it here. So these were the transition functions for the bidirectional associative memory we saw last time. And we saw that, I want to say something about being asynchronous and being synchronous, because we're kind of going to drop synchronicity from now on in this lecture, because this lecture is almost all about Hopfield networks. So what we saw here is that when you have a bidirectional network, this is the first layer and this is the second layer, with all the whatever inside, X units and Y units. We call nodes units sometimes, I don't know. Units is also like, for example, when we did the Mechalopix units or perceptrons were just like the ball with the threshold and the value. So when doing this and applying the matrix, what we do is that we simultaneously update the elements of one layer. So the synchronicity happens layer-wise, but the network jumps from one to the other. So the update of all the network is asynchronous, actually, because you update one and then the other. They don't get updated simultaneously. Okay, this is one thing. But in a BAM, we can actually also update one node. So we can also break synchronicity of the layer in some sense. So instead of updating all the axes, for example, like this, we take all the Y's and update all the axes. We can just pick one X, I don't know. Let's cancel the advertisement. Let's pick X3. And we just update that. What does it mean? I do as in the perceptron. So I do as the n of only the column of row. It's a good question. I don't want to write the wrong one. Yeah. W3 J YJ. So I can choose just one instead of all the vectors. And the rest stays the same. So I decide to update one neuron. Why do we say update? Because this defines a new value, but if the value that we obtain by performing this computation is the same as before, we say that we didn't update because the new value is the same as the one we had before. I hope this is clear. I used also a terminology that needs to be specified better, I suppose. So imagine in a BAM, I said I used the sign activation function. But I also told you, yeah, I can put weights on all those. But remember that I did the extended BAM when I used the weights, etc. So I can put weights. Let's write here. Imagine that this is x1, xn, and I put theta 1, theta n as thresholds for this layer. And on this other layer, I put p1, pk, where these are the units y1, yk. Actually, the y's and the x's are the value of the units, because the unit has the threshold and it's one. So imagine that I did that. Try to think about what happens when I do simultaneous update, because now the activation function is not SGN anymore, but it is the heavy side, either theta E or heavy side or P. So I cannot do this all at the same time because I have to do a different thing for each unit. Like, for example, x I plus 1 transpose equal to what? H theta 1 W. Like I have to put a different activation function for each component because each of these axes have a different activation function. So I just cannot just put SGN over this. Yeah, here should be a bit different. It should be this. But what I want to say is that when I have different thresholds, I cannot do things simultaneously. What I can do simultaneously is to calculate this because I can apply the matrix to all the y's. But when I have to put the activation function, I have to do a different things for each unit. So somehow I'm also kind of breaking synchronicity when I add thresholds, when I have different thresholds for all of those. And actually, that's also one of the reasons why we want to take away thresholds. Like I did the extended bidirectional associative memory last time, because if you take away thresholds, then we have all the same threshold 0. And so then you can do this all in one shot, putting heavy side 0. And then you calculate this, okay? So these blocks that I can calculate simultaneously for each layer are also called excitation vectors. Last time I think I defined this as E transpose. And each component of E is called the excitation of the unit X associated. I can call excitation also this, because it's the one that comes from the other side, and it is whatever I calculate before applying the activation function. Why this is important for what we're going to say today. So why, sorry. Yeah.
Question in the equation of x3, what is the subindex of y? Is it 1?
Yeah, here there is a mistake.
No, at the end, it's y.
He's asking about the index of y because it doesn't seem like a j.
W3j, y.
Yj.
J.
Yes, sorry, yes. Yj. The sum is over j that goes from 1 to k. W3j, yj. Not sure I did write that right. I hope it's right. But let me rewrite all this in once. This is gonna reappear, so if there was a mistake, we're gonna check it out. So, yeah, let me give names to these things. Last time I called this excitation T, but we call W, Y, E transposed. This is just because this is step E of the I of the computation, so let's forget about it. Let's do this, and let's do this. Go. Yeah, this is right. But so these things are calculated before the activation function. Let's make some reflections about the energy. All this is needed to talk about the energy. So let's go kind of back. I defined the energy at state x, y in the following way. Was without thresholds. So let's say the activation function is the sine function. It was xn, so This was the definition of our energy function that I gave you last time. Let's write down the W matrix somehow. Then you have Y transpose that has K coordinate. Now, you can see that kind of this is this, and this is this. So, we want to call this kind of the excitation from the left layer, and this is the excitation from the right layer, or vice versa. Like, somehow, this is whatever weights and values of X that come from here and go from some Y. So this is the excitation of the Y, the right layer, because it tells you for each unit in Y how much it comes from all the X's and all the weights. So if I fix, if I take the jth coordinate of this Y vector, Yi vector, it tells me whatever comes from this, all the X's and all the weights to this Y. So how much I'm exciting Y, I, and without calculating the threshold yet. And in the same way on this side, so I'm not, this is like the excitation of the left layer, because I'm taking, for each coordinate of this vector, I'm considering, without the sign, I'm considering whatever comes from this side with the weights to each of these layers before evaluating the threshold. So that's why these concepts are defined, also because they appear in the energy function without the activation function. So what is going on? Let's give names to this stuff. First, let's do the first one. So let's call this one, let's call this 2. I can write using 1, I can write the energy function in the following way. And I give names G1, G, and the GIs are called the excitations of the left layer. And this vector, I don't know, we can call it G, is the excitation vector of the left layer. The GI are the excitations of the I unit of the left layer. Okay. GI is defined as what? Whatever goes to the node I on the left layer before applying the activation function of that node. So J that goes from 1 to K, whatever comes from J, the J's, W1J, no, sorry, IJ, YJ. Yes. And using 2, so I multiplied it, like multiplication is associative, so I can decide to multiply this, so this is the same. I don't know, -1/2. That's the same thing. Yes. The object? Yes. Yes, here I was using 2. I did before the multiplication with 1. And here I'm using 1. Right. I did make a mistake. I'm using 1 because I'm using multiplying. Yes. I'm using 1 because I'm multiplying before these two. And here I'm using 2 because I'm multiplying before these two, matrix and what? E1, EK, G1, this is G transpose. Excitation vector of the left layer. Yeah, all this notation is just because we need it in the next proof. It's just terminology, or if you see it somewhere, it's that. Y1, YK. We write the energy in this way, and we say the excitation of the I unit of the round layer. Okay, that goes from 1 to okay. Let's take before it. Yes. N X N I X J. Right? I'm multiplying the axis when I do the G. Oh, no, sorry. No. One. Yes, this is correct. This is wrong. It goes from 1 to N. Y. K. Yeah, 3Y, X, J. This should be correct, hopefully. So, anyways, using all this together, this is the vector, this is the vector E. Using all this together, what we obtain is that the energy can be written in two different ways, either using the excitations from the left layer or using the excitation of the right layer. In the following way, either is minus some what is this? This is the second expression, either it's like so. What do we have to do now? This is some recaps from last time. Energy and energy when we have thresholds vector for the first layer and thresholds vector from the second layer. When the activation function is the heaviside step function of parameter, whatever is the index of the unit, is its threshold. So what I was saying before is that in asynchronous networks, we don't do simultaneous update. We just pick a node, we update that node, and then the rest of the network stays the same. So when we update a node, this is actually its excitation. This is GI. This is G3. So when I said the example before, this is X3, and I update it, I just calculate the excitation of 3, and then I evaluate. I don't know, this is the sign activation function, but imagine I add the threshold X3, so it's theta 3, because thetas are the thresholds of the first layer. This is just the side of the bits of G3. If I was on the other side, it would be the same. God, destroying everything. Okay, so this is one thing. And why do we care about asynchronous networks? Because the nature is not synchronized. People do whatever they want, whatever time. They do not decide altogether to do something. It's very rare. So they're mostly like, they're better models for like biological processes. That's why BAM is a good step from what we did before to Hopfield networks, because BAM can do both. Each of the layer is synchronized with itself, but the two layers are asynchronous somehow. So it's the jump between one layer and the other that is asynchronous. And we can also do within each layer asynchronicity. We just decide to do that, as I just told you. So yes, that's it. So now, again, I want to prove the convergence of the BAM to a stable state, because last time we saw that we can, like, the BAMs reach stable states after some iterations. You're gonna see that. You saw that in the exercises probably. Yes, exercises are also about like BAM converging to stable states. So it does not just jump from one to like, does not go wherever in the state space. The state space is X, Y. So it's depending on what you use as activation function, but the state space is the space where X, Y belong. So it can be -1, 1 at the power of n plus k. Or it can be -0, 1 at the power of n plus k. Sine function, Heaviside function. But yeah, so the network moves in this space, its state changes. The question is, after some iteration, does this like hit something as stays there? Hitting something mean finding a couple x, y, such that the network just jumps from that x and that y. So that couple is the state. So the network seems that it's moving, but it's actually always moving between the same two points that are the same point in the state space. So now we have to prove, to see that like this thing converges, we actually have to prove it. We just cannot say, yeah, this happens. So that's fine. And it is really important because like we know that the network will converge and will not like just run on the state space forever. That's something that the Hopfield networks can do actually, if we don't put any further assumptions. So the thing is that I was talking to you before about asynchronous update of the BAM, because actually the proof is the same. So either I update the full layer, either I update one node, the proof will be the same, because the update of one layer is just the update of all the nodes of its layer. So I will prove that the network converges to a stable state in a finite number of like iterations by doing asynchronous updates, and this implies that it holds for also synchronous updates. So yeah, this guy, let's come back after. Oh no, yes. So we have to prove this. Are you ready for this? We have to use that. That's why I put it there. It's not like the proof that I did 2 lessons ago, 3 lessons. It's a better proof. So I'm gonna prove it for updates of the X. So I pick just one X. One Xi, meaning the ith node, not a vector. I don't know, in the exercise sheets, the vectors were like bold. This is the vector at iteration I, but this is kind of like not the same. I'm considering just one node. I don't know if you remember the picture, one node. I'm updating one node and I'm checking whether something is going on. Let's. So, first of all, we start by saying that the activation function is the sign. We call the vectors x. And the state x, y, y1, y2. And this is the weight matrix. So the energy function is minus a half x w y transpose. It's a bilinear function, so energy in this case goes from sine, so -1 plus -1 at the power of n times plus -1 at the power of k r. What is a bilinear form? Not bilinear, but linear form, meaning that this linear is variables. If I put linear combination in x, behaves well. Linear combination in y, behaves well. Linear. And whatever is the state, spits a scalar. What is going on? Now I'm gonna recycle what's on the other blackboard. That's the whole reason why I wrote about this thing. So I told you that we can rewrite the energy using excitations. Since we're considering just x, we're considering just x. I don't care about this part. We rewrite the energy in this way. Using the excitations, like the excitation vector of the left linear. Because I'm updating, I want to update a node in the left linear, xi. Yes, so. Gi is the excitation of the ith unit, and is yes. So when I update, I want to update only xi, which is one of those. When I update xi, I put the activation function in xi, which is the sign, over this sum. This sum is, I don't know, y, y1, y1, plus 1, 5, 2, 5, 2, plus. Yeah, okay. I mean, it's actually like in the perceptron if you think about it, because this is, yes, so. When I update xi, I obtain xi prime, and this xi updated. That is the sign of this sum, so the sign of GR. Is the ith coordinate of the vector xi plus 1. What was said before is like, it's like x1 prime, x and prime. We name in this way its coordinates xi prime is this. From that one. That's good. So I wanted to update only xi. Imagine that I updated it. Means that xi and xi prime are different signs. So imagine either xi was xi1, either xi was -1. Is what the options. Imagine that I update it. If I don't update it, so now the question is, this was for the simultaneous update. So I update all the nodes in the X layer, but I can do also asynchronous update. I can call X prime the vector that is equal to the vector X for all coordinates except the ith one. So this guy is like X1, like the other one. But when you have the I coordinate, you have xi prime, and the rest is the same. So I just updated xi. Okay. So what I want to see is if the energy has changed when I did an update. Because if the energy, whenever I do something, goes down, means that we're going like reaching a minimum, and then I'm going to show that it's not minus infinity. That's the goal of this thing. I want to prove that updates lead to a stable state, so that the energy diminishes, and then I'm going to explain why the energy is not minus infinity. That's the idea. So when I calculate the energy of X, I want to see whether there is a relation between X, Y, and greater or equal, I don't know, of X, same Y as we change, the same fixed one. Of this new vector X prime, in which I just updated the ith coordinate and 1. Now, it's clear that if, when I do the update of X prime, GI has the same sign. So I don't know if for some reason I don't update, so if like this sign gets me the same signs I added in xi, those two vectors are equal, X and X prime are equal because I didn't update anything. So the energy will stay the same. Okay. But if I did an update, it means that X and X prime have different sign. No, I mean, x and x prime are already 1 and minus 1. So this means that if I update this means that x prime is different than x prime. So, and also that this implies that also the big vector is different. But so it means that one of these is 1 and one of these is minus 1, right? Now, so what happens with the energy when I update them? Let's try to write down the equation of the energy. So if I write the energy of x, y minus the energy of x prime y, what do I obtain? Minus 100. Do you see this is pretty bad? I change color. Okay, it's the 1 and 2, minus and minus is plus. I'm using the formula with the excitation vector. So I'm using the formula that I wrote somewhere here. You want to put R. Why the GIs are the same for both the cases in which I didn't update yet and now I updated. Because I update on the left layer. So the right layer, which contains all the Y's and the weights stay the same. I just changed 1 unit in the left layer. So this is x I prime. But I just said that x I prime, I don't know, I can call those primes and then say that x I prime is equal to xj prime is equal to xj for all j different from I. And I can say that xi prime is minus xi, because I said that they have different signs. They're different, but they're like minus ones and ones. So there is not too many options for being different. One is minus 1 and 1 is 1. So this holds true, so that x prime I is equal to minus xi. So this equation becomes more easy because I can just put everything together. The g's are all the same. So should I do this step? Yes. Yes, it's better. Sum of a j that goes from 1 to n, but j is different from I. J x I. I split the sums. I take out the 1. You can put the j's if you want to. Yes, minus 1 g I x I. Which is equal j by this. And then, so this is the sum of all the old ones, and this is the sum of all the new ones. The old ones, I put all the ones that are different from I together, and all the ones that I one alone. And I do the same for this one. So plus prime that is equal to minus xi. Why am I doing all this? I mean, you take this big sum, and this big sum, one is the opposite of the other. Because all the terms that are different from i's are the same, all the g's are the same. So I can cancel this part and this part. And I'm just left with two terms. Just left with two terms that are minus a half gi times xi minus xi prime. But xi prime, I just told you that is minus xi. So this is minus a half, this is plus a half. Got this there. Plus a half. Yeah. Minus a half gi 2xi's that is equal to just minus gi xi. Now I recall you that this is the difference between the old energy and the new energy. What is the sign of this quantity? I told you that, okay, xi prime, which was the update of x, was the sign of gi. So this was the sum of the weighted sum, like the weighted sum inside this sign. So since I updated, means that the sign of gi is different than xi. Is 1 minus 1. If the sign of gi is different than xi, if I multiply those, I obtain minus 1. They have different signs. One is positive and one is negative. So when I multiply them, I obtain something with a minus. So this is something that is negative. This quantity, because those two things, since I updated, have different signs. But it's something negative times minus, so it's something positive. What does this mean? That the old energy is greater than the new energy. The energy when I update just one node is smaller, so the energy is decreasing. Okay. So why does the energy whenever I update with time doesn't go to minus infinity? I can like reduce it. I'm strictly reducing it because I'm changing something. The equal holds just in the case in which my update gives me the same xi prime. But in that case, x prime, the new vector, is equal to x. Why does these things do not go to infinity? To minus infinity, sorry. It's decreasing, right? The energy is going to minus infinity. It can do that. So if you did that, then I have no argument to say this thing converges because the energy is just always updated. I want the energy to stop at some value, some minimum value. That's why before I was saying, yeah, energy, local minima, all these stories I told you last time do not hold in this case. So why the energy doesn't go to infinity? Minus infinity, sorry. What should I recall you? That our states belong to a set that is of this type. In the case of the sine function, but it's the same case with another activation function. And if you recall in the first class, I asked you the cardinality of this set, but this set is finite. So our system moves its state, I don't know, in a plane with finite numbers of points. And each point has its own energy that is fixed, calculated on that state. So it cannot go to minus infinity because it takes a finite numbers of values. So among those values, there is a minimum because the set is finite. Okay. Those are all, imagine that those are all the state, these are points in this set, okay? Our system iterates in this way with asynchronous or synchronous updates. But on all these points, I can calculate the energy. And so the set of energies, the set of all the possible energies, it is not a set, like it's a straight line. Yeah. For each of these points, let's say this is the energy. For each of these points, I calculate an energy. But this is a finite point, so I have a finite number of points here. So the energy has just a finite set of points you can take. So there is a minimum among those. I can calculate a minimum on a finite set. So the energy does not go to minus infinity. And so the thing at some point converges. That's the thing. It's a bit chaotic. Maybe you can have a look at the book if you want to see the proof. We're not going to ask you the proof at the exam. But I think it's important to see the proofs of some results because this tells you that the thing converges to local minima of the energy. And this is due to the fact that the state space is finite. And that at each update, the energy strictly decreases if the update changes the state of my node. What time is it? Time to a break. Yes, 5 minutes break. Are there any questions before that? Yes.
Then we have finite.
Yes, because of the energy of all your possible states is a finite set. So each of these states has a number associated with its energy. So the energy can just have those finite values. So there is a minimum in the set of the energies of your states. I don't know if it counts.
Yeah.
In the exercise, there will be like a concrete case in which you have like an actor and you like calculate the energy and you see that the energy are just like, there's just some value. Actually, in the next second alpha, there will be also an example with Hopfield when you calculate the energy of everything. So there is a minimum for the energy because that's all the energy, all the values the energy takes.
From that equation, minus half x W1 transpose, right? So
yes.
On that, if x and y has a finite dimension, then that cannot go to minus
Yeah, it's not just finite dimension, it's a finite points. Because you can have finite dimension, you can have Rn. And in that case, I don't know, because Rn has finite dimension, but you can put real numbers in the coordinates. Here, in the coordinates, you can just put 1 and -1. So you have discrete finite set of points. You remember again in the lecture in which I wrote the cube, that which was for example, -1, 1, or 0, 1, or 0, 1. 0, 1 at the power of 2, or at the power of 3. It contains just 4 points. So it's not just the finite dimension, it's the finite set of points. It would not work with Rn, I think. Like if this was Rn, I would say no. It's more difficult if it's like Rn. But here we are really like a finite possible set of states. Like our system is like a machine that moves among couples. Like one state is the couple x1, y1, another couple is x2, y2. It's like couples of vectors that are our states. But you have not infinite world. You can just move into 3 islands. You jump between a finite set of points. And that's the argument for this. I think it would be way more difficult than false.
For Rn, like any value in about minus 8, so then this one. So for this case, I think +1 and -1, so then 1 go for minus infinity when dimension is 5. In Rn, they tend to go to minus.
Yeah. Remember that Rn has finite dimension is n.
But inside that is
Inside, but yes. So the problem is that the degree of freedom you have to move in your state space that is bigger. But probably it holds true of putting other assumptions. I don't know, but it's possible. Reading just XR. You see that this GI, that is the excitation of the unit XI of the left layer, it's like in the perceptron model. So we're taking whatever comes from here and putting it here. And this is the excitation. So whatever comes from this to the weights that are at index I. This is the interpretation of GI. It's whatever this is before passing the threshold. So I think this is a bit better. I thought I did a mistake in the proof, but there isn't. So yeah. I thought I mismatched the index, but it's right. It's fine. Now, thank God we go to Hopfield networks. But yeah. But it's kind of similar because the main idea of the Hopfield network is to do asynchronous update all over the place. Like we don't talk about synchronicity anymore. Again, I showed you before the photo of this guy. That is the guy who won the Nobel Prize today. So this year, not today. But for physics. So what the hell does this have to do with physics? So let's try to understand what's different in Hopfield networks. It's a bit different from bidirectional associative memories. So that's why we need to understand what is going on. So we have a set of units, n units. And the updates are only asynchronous, meaning that I have this set of units. There are not groups of units that constitutes layer. There is no layers. There's just units all over the place. You pick a random unit. Okay, and you update it. So as we did here in the BAM, but for a set that in which units do not belong to layers. So the states are vectors X. And we chose that we belong to -1, 1 at the power of n. Again, we could choose 0 and 1 and then normalize, we don't care. And that's why actually the activation function is the sign function. Or this kind of weird Heaviside step, like it's a mixture of like Heaviside step function, but I want the output to be -1 and 1. I could have done this last time, yes. There's a mistake, so very cool. Yeah. So I have to re-update the slides. So the function is wrong on these slides. The function I wanted to write is this, f theta I. So there is also a threshold vector. I can put a threshold to any of those nodes. I don't care. And the function is the following. So it's like the Heaviside step function, but has -1 instead of where I wrote 0. It's 1 if x is greater or equal than theta I, or if x is smaller than theta I. Of course, we can write this as a function of the Heaviside step function in this way. So we can say that the Heaviside step function of threshold theta I x is 1 plus f. I showed you this last time. So basically, if I'm bigger than the threshold, I put 1. If I'm smaller than the threshold, I put -1, bigger or equal. Also for the equal, we can decide, it's like the sign function, like what you do for the sign of 0. Either you arbitrarily say it's positive or you just don't define it. There is some people who don't update the unit if the sign is zero. So if you end up in zero, you just don't do anything. It's an arbitrary choice. And let's make this choice. And so it's clear what this is. I will correct the slide soon. So since I have n units, I have a square matrix. Now, what do I even have to talk about a matrix if my updates are not synchronous? So this is called the connection matrix. And before it was a transition matrix. I don't use this to do the transition simultaneously. I just use this matrix to store what's in the weights. Like all the weights, I have to put them somewhere, I put them here. So it's a square because it's m times n. Do I have to write it? No, you have it there. So connection matrix or weight matrix. So this is an example of Hopfield network. I have 3 nodes, 3 units. Edges are bidirectional, meaning that to go and to come back, I use the same weight. So this means that Wij is equal to Wjr. And what's the link between this and the bumps? It's kind of weird. And I have thresholds, different thresholds. I note the thresholds on the nodes, and I say the name of the node, the value of the node outside, kind of like before. How does this thing work? So each unit is a perceptron. So I pick a unit, UI, a unit, and we updated the value in this way. It's not insane. I just take whatever is going into my eye. That's probably not. This is W12, this is W3, and this is W13. Okay. What do? I pick a random unit, x2, and I update it. Its value before can be either -1 or 1. So what I do is that I take all the excitation coming from the other ones, I do the weighted sum, and then I check whether it passes the threshold or not. If it passes, it will be the new value of x1, x2 will be -1, so it will be 1, otherwise it will be like -1. So I do f of that f that I defined before, theta 2, x1 w12 plus x 3 w23. Is that all right? I pick 1 and I update it. So I don't know, before my state was 1, 1, 1. I picked to x2. So imagine that this gave me a -1 from this computation. So I transition by updating x2 to a new state in which 1, -1, 1, and so on. I do updates and I pass to another vector. I'm moving inside -1, 1 at the power of 3, as we have seen before in the proof. My network transitions randomly because I randomly pick at something to another one. And I can also explore all the possibilities. Imagine that I start from this state. I can ask myself, what happens if I update x1? I will transition, I will stay here. Imagine that if I update x1, I stay here. I just write it like this. And if I do x3, I transition. Imagine. I transition, so I click 1 to 1. And so on. I can explore all the space. I can write all the vectors in this space. And I can say, if I start here, where do I go when I update everything? But the updates are random. And I don't do 2 updates simultaneously. It's not that like I can update this and this together. Doesn't work. So this is the way these machines work. What's the relation to the BAMs? Historically, those things were invented before the BAMs. But yeah, there is a relation, of course. You can see that. So the matrix is squared. So you have to say that n is equal to k. And then you have to see that every yi, you make it coincide with xi. Because I told you that the asynchronicity was between the layers. So I just make the layers coincide. So I don't know, need some time to think about it. But like the way this thing transitions can be similar to one of those in which the layers have the same size and which you have identified the one with the same index. But yeah, it's not a big deal. We just pass through the Hopfield model. So the units in the Hopfield model are called totally coupled, meaning that each unit is connected to all the others. It's like fully connected in the neural network literature. It's connected to all the others but itself. I don't have loops. I don't have this with a weight. It doesn't happen. Also, meaning with the parallelism with the BAMs, it means that also the horizontal lines are gone, like W11 and stuff like that. The edges are bidirectional, meaning that I can go back and forth with the same one. So Wij is equal to Wji. And the weight matrix is not used as before. So we don't multiply the matrix by the state in some way. We don't do this. This is over. We just do one node at a time. Why all this? So clearly, like these first two things that I said, being totally coupled and being bidirectional, put some constraints on the matrix. Why do we need these constraints? So those constraints are symmetry, because this being symmetry. A matrix is symmetric if in the diagonal I can put whatever I want, but this part is equal to this part. Okay, it's equal to its transpose, whatever, however you want to say it. This is another way. Symmetry is due to the bidirectional edges. And zero diagonal means absence of loop, like of things that go from to itself. So why these assumptions are important for convergence? What if I don't have those? So let's start with a stupid example and see what happens. Try to write down it by yourself. So if I make a mistake, you can see it. So what happens is that what is the state space, first of all, when I have that matrix? So I'm dropping zero diagonal. So I put -1s on the diagonal. How does this machine work? I don't have thresholds also. I assume that the threshold is a sign function here. Also, this weird f theta function, when you put theta equal to 0, is the sign function. That's why I introduced it. Yeah, what I just said is that f0 of x is equal to s dn. So we assume that we are in this case. So we have the weight matrix that is -1, -1, 0, 0. What is going on? I have two nodes. The threshold is 0 and the threshold is 0. So the weight matrix tells me how do I go with what price. So I stay in x1 with price -1, and I stay in x2 with price -1. I don't go from 1 to 2, and I don't go from 2 to 1. So my updates have the following form: xi x1 is updated in the following way if I update x1. as Gn of x1, 1. Right? Because the other term is 0 plus 2 plus, sorry, 0 times x2. So I told you that these machines move in minus 1, 1 at the power of 2 here. So let's write all the points down, see what happens. This is 1 point. So imagine I'm in the state 1, 1. And I update x1. I update x1, meaning that I do this. x1 is 1 minus x1, so I transition to this. If I update x1, the new x1 is given by the sign of minus x1. So I have 1, sign of minus x1 is minus 1. So I'm flipping my x1 minus 1, and x2 stays the same. So if I update x1, I transition to this state. What if I update x2? x2, the rules of updating x2 is the same as Gn of minus x2, because 0 is the coefficient that multiplies x1. Again, x2 is 1, so I'm flipping its sign. So if I update x2, I go here. Right? So imagine I'm here, and now I update x1. What happens? I go here. Because updating is just changing the sign with these rules. That's what this matrix is telling. So if I'm here and I update x1, I go here. And if I'm here and I update x2, I come back here. Again, if I'm here and I update x2, I'm changing its sign, so I go here. If I'm here and I update x1, I go back here. If I'm here and I update x2, I go here. And again here. So basically, I'm always moving randomly. Whatever I update, I will never stop anywhere. I will always move cyclically. So this thing doesn't converge. That's why we can't. That's why like having 0 in the diagonal is like necessary condition for convergence. It's not sufficient, by the way. All these conditions are not sufficient yet. We will see next time what's needed for like assuring convergence of an optimal network. In this case, the network moves randomly on those 4 points. Because if I'm here, I can go here or here. I never stop. It does not go somewhere. A converging network, like the arrows lead you somewhere. We will see some cases. But this is a case in which it doesn't converge. So that's why we don't want that. I hope it was fine. Are there any questions? Online people. Okay, let's move on to another example then. Let's drop, so if there is 0 on the diagonal, I can also put, when I update, instead of just making the sum, this is the sum over in all the indexes, I can exclude I, because WII is always 0. So I can rewrite the way this algorithm computes in this way. But yeah, it's just useless crap. If it's 0, you just put 0. So what happens if I drop symmetry? So I put 0s on the diagonal. Let's write an example in which I drop symmetry. That's So let's drop symmetry. W is now, I don't know if some of you ever did Hamiltonian mechanics, but this is the symplectic identity. The J. I don't know if mine is always here, but yeah, this is like that a lot. So, this is it. How do we compute the updates? So xi, x1 in this case, is equal to sine. So the network is this. This is x1 of threshold 0. And this is x2 of threshold 0. I go here, from here to here, with price -1, because this is W1, 2, this is W2, 1. And I go from here to here with price 1. So when I update x1, what I do is I do the sign of what? Minus x2. And when I update x2, I do the sign of x1, right? That's what this matrix does. What happens on the state space? X1, 1, minus. This is 1 minus 1, and this is minus 1 minus 1. What is going on? If I start from here and I update x2, I start from here and I update x2, gets the sign of x1. It wrong. Want to change my plans. X1. Oh wait. Sign minus x1. Sign. Yes, this is a right. Yes, let's write it all. Right. This is y. W2, 1, x2. So this is sign of x2. And this is sign of W1, 2, x1. So this is sign minus x1. So if I update x2, sorry, if I update x1 here, we stay here. If I update x2, I go here. If I update x2 here, I stay here. If I update x1, I go here. I update x1 here. You can verify those by yourself and check if I made a mistake. Update here, I update x2. This one. Yes. Do you agree with this? Did I make a mistake on purpose? Maybe. So x1 takes the sign of x2, and x2 flips the sign, takes the opposite sign of x1. Let's also pose another. So yeah, I made no mistake, I think. But what does this network do? Does this converge? Does this converge? Nope, because it goes all the way around or it stays here and then it goes all the way. It doesn't like go anywhere. There is no arrows that always all point to a state. It just moves randomly. However I choose to pick, whatever sequence I can choose a sequence of like 1, 2, 1, 2, whatever sequence of random numbers of 1 and 2 to move in this graph. It will go anywhere. Like it will just like move and like will not converge. And this is due to the lack of symmetry. So symmetric matrices and matrices with zeros on the diagonal are necessary for convergence. Okay. This is the definition of the energy for the Hopfield model. It's the same as before. I put X instead of Y. Since the matrix is squared, I have the same size of vectors on both sides. And the expression on the other side is just like the development of the computations, let's say. But this is the definition of the energy. And also you have the definition of the energy when you have thresholds. And this is the same definition of the energy with thresholds. But we just did the thresholds of the nodes, because before I had the thresholds of the left and the right layer, and just now I have just thresholds. Yes. We can say that the energy is a quadratic form, if you heard before about quadratic forms, which is a little bit more of a bilinear forms. So you have like a bilinear form with the same vector on both sides, because we can do this for a squared matrix. So this is just more of a historical, cultural, whatever. You have more details on the book about this, but basically Hopfield models were discovered to be isomorphic to what is called the Ising model. The Ising model is done because there's people among you who do material engineering. Is that correct? So this is about ferromagnetic materials at temperature 0 have a deterministic behavior that can be modeled with a Hopfield network. So the magnetic, whatever orientation of each particle, there's just 2 options. So you can say that is the state of that node. And you can say that the weights are the way the particles interact with each other. And the thresholds is the magnetic field. So if you go to the energy, there is like a way of like gluing the energy, the second equation of the energy, to the equation like in a magnetic material, like, sorry, in a ferromagnetic material. So, and this like drops when you don't have temperature 0, because what happens is that there is a stochastic behavior when you have some kind of temperature. So transitions are not anymore deterministic, but there's a probability that an update will occur, whereas in this case, if I update that, it will update it. This is deterministic. That's what it will give. When I write an arrow here, I said, okay, if I update this, I go here. In a stochastic case, I go somewhere with a certain probability. So I transition with a certain probability. So, but you have more details. I'm not like an expert at all in this. So you can like, I know people that their PhDs in these topics. So like there's a lot of stuff going on. But just to say that there is like applications that are direct applications of the Hopfield model. I mean, there's a reason why the guy got the Nobel Prize. Yeah, so let's do an example that works. So like a simple example again, but one where the assumptions hold, the way you have the time, yes. Let's change the matrix and see what happens. Let's change this. Now I will make a mistake. You have to find it. So. So this is an example of a flip-flop. I suppose is this something in electronics as well? But I don't know anything about electronics, so I'm not going to talk about it. But I suppose you can make the link if you know that stuff. But yes, so yeah, let's write it before I can see. Okay, so this is x1. We put trajectory equal to 0, and I said that this is -1. So the weight matrix is what? I cannot go from 0 to 0, but I can go with -1 and -1. This is the weight matrix. What happens when I do updates? How does this network update anyways? So x1, x1 is updated using this. And x2 is updated using this thing. Let's go. And here I update x1. What do I know? X1 takes a sign of -1. So x1 is flipped to -1. X2. What happens if I update x2? Like this. What happens if I'm here? If I update x2, I go here. Because if I update x2, I take sign of -x1. x1 is -1, so I get 1. So I flip the -1 to 1 here. And this happens if I update x1. And whatever I do here, I stay here. x1. So this is an example of a network that converges. Converges to what? These two states, depending on where I start. If I'm here, I will converge to here with one certain probability. Like if I'm here, I will converge to here if I update x2. But if I update x1, I will converge to here. And whenever I end in a state that is a stable state or a fixed point, I stay there. Whatever I do and in here, I will stay here. Same. So stable states are x1 -1, 1, and 1 - 1. I suppose it's called flip-flop because the stable states are the ones that are like an interrupter. So either it's one like this or it's this. Of course, it's related to the electronic ones. I don't know how. We also say that a network stores its stable states. It's like the stable states of a network are the relevant information about its network. So there's this terminology that is adopted that is a network stores its stable states. So now I told you all that crap about the energy in the first hour. So let's calculate the energy of this thing and what is the energy of stable states. Since we just have 4 points, we have to calculate 4 numbers for the energy. So it's not a big of a big deal. What is the energy? X, E of X, because it's just X, is, do I have to do all the computations? Okay. There is no treasure, so yes, X1. I'm skipping some points. It's the product of X1 and X2. So what is the energy? Okay, let's see. I apply the energy and I put all the numbers instead of this. So the energy is 1 here, -1, -1, 1. So the stable states are minimal for the energy. Because this is what we were asking before. Like you have a finite number, sets of values of the energy. So the energy can just be this. Actually, the energy is just 1 or -1. And the local minima, the global minima. Sometimes it's local, so don't trust. but the global minima in this case are -1 and 1 that are the stable states. So in this case, stable states are minima for the energy as in the bound. Boom. This is the yes, but in R3. So you have x1, x2 in the plane, and on the vertical axis you have the energy. And you can see that this is for like taking values in R, but clearly our function is taking like the domain is like for just 4 points. So you just have to count the points. And you see that the 2 points that are stable states are the minimum, and those 2 spikes down. That's pretty cool. So he said to store its stable states is something that he say. Okay, now I don't want to prove convergence of the Hopfield network today because it will take too much time. But now we can do the logical functions as we did in the first lecture. Because there is some equivalence between perceptron models and there is an equivalent Hopfield networks. There is also this result that there is equivalence in power, you can compute something with the perceptrons, there is an equivalent Hopfield network that does the job. So can we do that for logical functions? Yes. To do that, so I want to do the OR today. You will have the AND as an exercise. And the XOR, of course, is problematic because it was problematic also before. So we have to assume some things. Now, the states are +1s and -1s, and before were 0 and 1. So we have to say that true is 1 and false is -1 instead of 0. It's not of a big deal, but the thresholds will be different and stuff will be different. And also we have to assume another thing, that I told you that we pick units randomly and we update them, but we can also choose a priori, first part of the algorithm, never update x1 and x2. We say that those are clumped states, so are states that I decide not to update. And in this case, x1 and x2, that is, I want to do x1 or x2, as you see in the picture, are the ones that I don't touch. If I don't touch them, it means also that I don't care about the edge between them, and actually don't care about the threshold because I never update them. So what I'm doing here is so for logical function, we have -1s and 1s. Meaning that the truth table of the OR, I have to write it, I'm sorry. What I want it to be is this. So pay attention that when I ask for a network that does the OR, I mean that a network that stores the truth table of the OR as its stable states. So this network has 3 neurons. I recall you what was the network before, x1 and x2. Remember in the past, our nice memories. One that was the McCulloch page. It's also a perceptron because we don't have weird edges. It's everything you want. It's one. And now it's kind of weird because I have 3 things here and I want 3 things here. X. What? 1. I never go here somehow. I don't care about this. I have to put a threshold here. So there is no output in Hopfield network. The information that it's stored, it's set of stable states. So I want a network such that those, so it has 3 neurons, so it means that it's a network that runs in -1 at the power of 3. So my set of states, I'm going to write a list because it's 1, 1, 1. To the power of 3 elements. So I have all these states, and my network moves this. So the question of having a Hopfield network that models, computes the OR, means that having a network that whose stable states are those. So what's now? Let's explain why that network is the OR. They put 0.5, but actually every number that is between -1 works as well. That's every number between probably 0. Let's do the sum. This is 2, this is 0, this is 0, this is -2. This is the weighted sum of the excitation coming from those, because I put 1 and 1 as weights. So the only factor I update is x3. And I update it in the following way. I do f of theta, whatever theta I decide to put, of the sum x1 plus x2. And I want this truth table, however the values of these works, right? I want the truth table to be the one of the OR. So what do I put as threshold? Whatever that goes from is strictly greater than -2. Zero and 2 is fine. Whatever theta in that interval is fine, including 0, because by f has greater equals theta. But let's try to compute this machine so to see if we trust it. What if I start from here? We do the same thing, but with all these states instead of just having 4. I start from here. I update x3 because x3 is the only thing I can update here. So I update x3. What do? I consider 1 and 1. I do the sum. That is 2. It passes the threshold. Imagine that I put the threshold as in the book, -0.5. It passes the threshold, so I get 1. That is its value. So if I'm here, I stay here. x3 is the only thing I update. So this is a stable state because I don't update anything else. So if I'm here, I stay here. And you can prove that if I'm here, I will actually go there. So let's put together all the states that have the first 2 equal and the third different, because the third is the one that they can change. So those states are put in couples, like this is a couple. There it change the couple. That's this. So you can see that there are 2 similar. Yeah.
Third and fourth.
So they go in couples, and you can check that in each couple there is one that is a stable state and the other one goes in the other one in the couple. So overall, the set of stable states is one of the states in each of those couples, and whenever I am in another one, I will go this one.
3 and 4 are still the same.
There's a problem here, wait.
Yeah, they're the same.
-1. So I can tell you which ones are the stable states and are the ones that are the truth table of the R. So this is the stable, so let me go with the. This is the stable state. This is the stable state, and this is the stable state, because not false and false gives false, and the other one goes, sorry. Whenever I am in the other one, I will converge to this one. So that's it. I think it's over. Yes, I don't have anything else. Are there any questions? Are we over time? 5 minutes? Yes. Damn it. Sorry about that. Next time we will do less.